Alright, so we're back. This is going to be a video on the derivative and antiderivative of e to the x, and I'm going to show a proof on how to find the derivative of it. So quick review before we start. E is equal to the limit as n goes to infinity of the quantity 1 plus 1 over n to the n power. And you might remember this from the compound interest problems in your previous math classes. If not, you're probably going to want to watch a video on what E is all about. But what we're basically going to be doing with this E is using it as the base for an exponential function and finding the derivative of it. So here we go. Alright, so to find this derivative, we are going to use the limit definition, which is going to be equal to the limit as h goes to 0 of e to the x plus h minus e to the x over h. If you do not remember the limit definition of derivatives, I highly advise watching the video just to kind of relearn and give yourself a review of what the limit definition is. But this is what it would look like if we were applying it to the e to the x function. First thing I'm going to do is simplify this up here using our exponent properties. So you'll end up with the limit as h goes to 0 of e to the x times e to the h minus e to the x all over h. Okay, from here I'm going to factor out the e to the x from both of these terms. So you're going to end up with e to the x times e to the h minus 1 all over h. This e to the x is not affected by the h going to 0, so I'm actually going to pull this out and put it in front of this limit notation. So you'll end up with e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Okay, this term right here, I'm going to put a box around it. You can solve one of three different ways. One way is you can just plug numbers in for h that get closer and closer to 0 and see if you notice a trend of what it's getting closer to. So it's getting closer to a certain number but never actually reaching it. That's one thing you can do. Two, you can graph it. So if you graphed this right here and then looked at where h is getting closer and closer to 0, so say h is your x, as it's getting closer and closer to 0, you'll see the number that it's getting closer to. Okay, so I'm going to actually do this right now and show you a graph right here. Okay, as you can see from this graph, as h is getting closer to 0, the limit, the function, ends up becoming equal to 1. So this whole thing right here in the box ends up being equal to 1. So 1 times e to the x, it would get you to be the derivative of e to the x is equal to e to the x, which is correct. Now there is a third way of doing this, which is going to be to do this algebraically, and that's what I'm going to do right now. Okay, the problem with doing this algebraically is we don't know what e to the h is. Okay, there's a way of simplifying this right here to be able to solve this algebraically. So I'm going to use our definition of e up here to do that. Okay, first thing I want to do is, this is the limit as h goes to 0, and this is e to the h. Up here I have n's, n going to infinity. I'm going to substitute that with h. Okay, now to do that, I'm going to do n is equal to 1 over h. So now I'm going to substitute this 1 over h in appropriately here for the n's. So I'm going to have e is equal to the limit with a quantity of 1 plus 1 over n is going to be 1 over h, which is equal to h, to the n power, which is equal to 1 over h, like so. Now this n going to infinity, if n is going to go to infinity, then that means that you should be dividing by some number that's getting closer to 0. So that means we should be doing 1 as h, 1 divided by h getting closer to 0. So that means instead of n going to infinity, I can just write h is going to 0, because it's the same thing as n going to infinity in this case. Okay, so now our limit as h goes to 0 matches our limit as h goes to 0 over here. Okay, now I need e to the h. Well, I have e right here. I'm going to raise both sides to the h power. So I'm going to put this in a little bracket here. H goes to 0, 1 plus h, and it's being raised to the h power. Now, these h's will cancel because you can multiply the 1 over h times h when you have an exponent of an exponent, and it ends up canceling to 1 because h over h is equal to 1. So from here, I'm going to simplify, and you end up with e to the h is equal to the limit as h goes to 0 of 1 plus h. So now I can substitute this 1 plus h in for this e to the h right here, because e to the h is equal to this, and the limit as h goes to 0 matches. So that's what I'm going to do. So this is going to be equal to e to the x times the limit as h goes to 0 of 1 plus h, put that in parentheses, minus 1 all over h. Okay? This simplifies nicely. We have 1 minus 1, 0. H over h is 1 over 1. So you end up with this whole limit right here being equal to 1, just like I got over here and with the graph. So you end up getting e to the x times 1, which is equal to e to the x. So the derivative, I'm just dropping this down now, of e to the x is equal to e to the x, which is the main point of this video, to prove the derivative of e to the x. And it ends up being itself e to the x. So while we're here, we might as well find the antiderivative of e to the x with respect to x as well, and you end up with e to the x plus c. And you can test this by taking the derivative of this, which would be e to the x, this constant would go to 0, and you'd end up with e to the x based on this over here. So here is the derivative and antiderivative of e to the x with respect to x. If you have any questions about anything in this video, let me know.